Okay, good morning, Year 13 Calculus. Today we start a very important step, the difference between an indefinite and a definite integral. Okay, now so far we have been playing around with indefinite integrals. Indefinite because we always have to write a constant of integration after the integration. Okay, so let me just summarize a few of what you already know about what indefinite integration is about. Okay, now these integrals are those that change the gradient function back into the original function. Okay, and these are the integrals which, after integrating, must always have a constant of integration added. Now, I think you should know by now why we add this constant of integration, because although this one here, in this example here, 6x squared, this 6x squared is the gradient function of this function here. Okay, so when I differentiate this function here, 2x cubed, I get this 6x squared. So this thing here is the gradient function of this original function here. The reason why we have to put this plus c is because we don't know if there is a pure number here. Like it could be 2x cubed plus 1, it could be 2x cubed plus a million. We don't know what that constant is. So when we integrate back to the original function, when we go this way back to the original function, we have to have this plus c there, so as to say, yes, there could be a constant that disappeared when we differentiated. All right, now that's the basis of indefinite integration. Okay, now what in that case is definite integration? Now these, and I'll be showing examples of this fairly soon, okay, but these are the basic ideas that are behind definite integration. First of all, these are integrals that can calculate real areas underneath the curves, okay? And these integrals, they have no plus c after the integration. So you do not write plus a constant when you've finished your integration. And these integrals must always have what are called the limits of integration. Okay, now I will explain all of that in an example in a minute. I'm going to show you one now. I'm not going to explain it completely because I'm going to go into some detail about this in a minute. But this is what they look like. These two things here, this 0 and 5 at the top and bottom of this integral sign, these are called the limits of integration. And you integrate things like this, and you write the proper thing there. It's be 2x cubed. Okay, it's the same function here that I'm integrating 6x squared. I'm doing the same thing there, and you get 2x cubed. You get 2x cubed like that, and usually you put it in square brackets like that, and you write the limits of integration there and there. Well, when you work this out, you get the answer. You can't quite see it there because my pencil's glaring in the lost in the glare of the light. It comes out to 250 units squared, and that stands for a real area underneath the graph of this from x equals 0 to x equals 5. Now I'll explain all that in a second, okay, and where this 250 comes from. I'll show you how to do that in a minute. But first of all, I want to try and show you how definite integrals can be so powerful, because it was like meeting head on a real problem that mathematicians battled with for centuries. Just look at this diagram here on the left. This thing A, which I've called, oh, sorry, A stands for the area. You should recognize this shape as a trapezium. And of course, if it's a trapezium, then all four sides are straight. And here we have the sum of the parallel sides, A plus B, and we add them up and we take a half of that, and then we multiply by the height, or in other words, the perpendicular distance between the two parallel sides, which in this case is this thing here, the height. Okay, and we use this formula to find the area, and it gives us an exact value. Okay, we've got this one side here which is straight, but nonetheless, using this formula, we will get an absolutely precise value for the area of that trapezium. But what happens if one side of the trapezium is bent? Here we have a curve. Here we have the curve going the other way, like that. Okay, the area of that shape, of course, will be a little bit less than the area of that trapezium. The area of this shape, of course, will be slightly more than the area of that trapezium, because the curve bends upwards like that, it bends outwards. Down here it bends inwards, so that we're losing a bit of area. But the problem is, how on earth do you find the area of a shape like that, where one side of which is not a straight line like that, but is bent? It's a curve. Well, this problem, it plagued mathematicians for centuries. And it was only when the calculus and definite integration was discovered that people worked out exactly how to find the area underneath curves like this. And that's why calculus, and especially this definite integration part of calculus, is so powerful, because it gives us a way of precisely calculating areas underneath curves like that. Okay, if we know the formula of these curves, of course, the functions. Okay, so let's see how that works. Now, first of all, I'm going to zoom back out and go to the next page. Next page is there. Okay, so let's zoom in and talk about this. All right, now where we are, where are we? Yes, there we are. Okay, now in this very first example, what's that? In this very first example, I've got a curve doing this, and it looks like some sort of, curve, and I've called it y equals x squared. I suppose this little taily piece here shouldn't have gone like that. It should have gone like this. Okay. Yeah. So I want you first of all to imagine we've got a triangle that goes like O to A to B, O to B, like that. So we've got this triangle, and we're trying to find the area of the triangle. Well, the area of any triangle is half the base times the perpendicular height. Well, the base here is from 0 to 4. Okay, so we go half of 4 times the perpendicular height. Well, we get the perpendicular height because we know that this function is called y equals x squared. So in other words, we put 4 into this formula here, and we work out that y's value must be 16. 4 fours are 16. So we know the perpendicular height of this triangle. Okay, and if we do that, we work out that the triangle OAB is 32 units squared in its area. Okay, so if we want to ask the question, then what is the area underneath this curve? Okay, between 0 and 4, it must be a little bit less than 32 units squared. because the curve goes below this straight edge of the triangle, the straight side of the triangle. It drops below it like that. And so the area, this red shaded area here, must be less than this 32 units squared. Well, how do we do that with definite integration? Well, what we do is this. We say that the area under the curve from 0 to 4, you write it like this. You integrate and you put your limits in, these two limits here, 0 to 4. Now, it matters very importantly that you put the smaller limit always at the bottom and the upper limit at the top there. So you're integrating the function x squared, and of course if you do that you will create the function x cubed over 3. You increase the power of 1, divide by the new power. This straight line here says that we've now got to insert the limits 4 and 0 for x, and what we do is the following. We first of all, the first one you put in, the first limit is the upper limit, the 4. You put it there in place of the x cubed. So that becomes 4 cubed over 3. You put this in brackets, and this is always a minus sign. Okay? A minus sign. Now we put the 0 in place of the x cubed. Now I've written it there, and of course 0 cubed, that it's going to make all of that 0, but I've written it in just to show you what we do with the two limits. We put the upper limit here in place of x, and we take away the lower limit in place of x here, and we work it out. Well, all of that disappears, and this one becomes 4 cubed. Well, 4 4s are 16, and 4 16s are 64. So it's 64 over 3, as you can see there. Okay, 64 over 3, which is 21 and 1/3 units. Go away. And you can see that this 21 and 1/3 is indeed less than the 32 units squared, which is what we expect. But I just want to point out, look what it can also now tell us. If we go back to our diagram, we can see that if this red shaded area underneath the curve is 21 1/3 units in area, and we know that that triangle, the full triangle, is 32 units squared, when we take the 21 1/3 away from 32, we get this dotted area in between the straight line and the curve, this one there. So you can easily use integration to find the area of rather strange shapes. There it is. But look what this also tells us. It tells us, lets us calculate the area exactly of that shape there, this OA and this bit between the curve there and that straight line there, the triangle, which comes out as 10 2/3 units squared. Okay, now I know it says example 2 down the bottom. Well, I'm going to let's see if I can fit it in. No, I'm not going to do that now. What I'm going to do, because I'm running out of recording time, okay, so I'll do that on a separate recording, okay, because we need to try and knit all this together a bit better. Okay, thank you very much.